While the world chases loud, chaotic noise, the quiet architect optimizes with absolute precision. True optimization requires no unnecessary noise. The quiet architect operates on pure intellect.
Inside a modern biotech lab, the hardware moves with rhythmic precision. From the outside, the entire automated operation appears to be executing flawlessly. This is the view from the executive dashboard. The central servers are humming, the data is flowing, and every indicator light is green. But the quarterly P&L tells a different story. This chart shows the gap between projected revenue and the reality on the ground, where actual yield takes a sudden dive due to a wave of ruined assays. When the C-suite audits the system logs to find the source of the failure, the software reports a perfect record. According to the digital history, every single robot performed its task with 100% success. The digital record is perfect, yet the physical product is gone. It's a contradiction that suggests someone or something is lying. This specific discrepancy is a symptom of a wider industrial pattern. Analysts call this the trillion-dollar blind spot, a systemic disconnect where executive data reliance and ground-level physical execution move in two completely different directions. Trusting these logs blindly allows a structural hemorrhage to continue unnoticed. To find out why the batches are failing, we have to look past the dashboard and investigate the hardware itself. The truth is usually found on the lab floor at 4 a.m. This is where the quiet, undocumented labor of the night shift happens. These technicians often bypass the automated reports. They are already pulling the ruined batches by hand because they can see what the software is programmed to ignore. The failure is often microscopic. In this case, an automated plate handler missed a single microliter of reagent, a mistake that effectively voids a $1 million assay. This error remains invisible to the boardroom for a simple reason. The system is monitoring the commands, but nobody is watching the robot's physical hands. To understand why this happens, you have to look at the mechanical logic of the robotic armature. A pipetting robot is essentially a fast idiot. It is a machine that executes complex electrical commands with high speed, yet it possesses no internal mechanism to verify its own physical output. This logic tree illustrates the disconnect. On the left, an electrical signal perfectly completes its circuit, but on the right, the physical fluid fails to detach from the tip. Software registers intent, but cannot verify fluid dynamics. Because labs rely on cloud processing, a latency gap forms. Relying on post-batch logs instead of real-time local feedback means a single microliter mistake creates a cascading disaster, ruining every downstream process. The solution is a physical intervention. We mount low-cost cameras directly onto the robotic armature. This is the foundation of restorative engineering. We deploy Python-based edgeai vision directly on the device to give the machine eyes. The system processes every visual frame at the exact point of mechanical contact. It monitors tip attachment, volume, and plate alignment in real time. Because the processing is local, the system can halt the machine the milliseconds an error is detected. This prevents a single mis-pipette from compounding into a ruined batch. This application of AI focuses on high-stakes, practical mechanical troubleshooting. It also challenges the industry myth of the fully autonomous self-driving lab. When dealing with delicate biological arrays, hybrid human-machine control is the only mathematically sound approach. True operational efficiency comes from restoring agency to the people on the floor, by giving the machines the ability to see. To protect the enterprise, you cannot just trust the log file. You have to watch the hands. $10 million automated bioreactor array is currently executing a massive, complex sequencing run completely in the dark. The central software system records every electrical command sent to the machinery. Right now, the system log reads, "Operation successful," but the physical reality on the lab floor is an empty tip. The robotic armature just missed a microliter of reagent. Software registers electrical intent. It cannot verify actual fluid dynamics. Because nobody is watching its hands, this microscopic physical error at step 1 silently destroys million-dollar downstream assays. That single missing microliter trickles upward. Weeks later, it manifests as a massive financial hemorrhage on an executive's profit and loss statement. The left side is a digital dashboard recording a perfect electrical command. The right side is the unverified, chaotic reality of fluid mechanics on the floor. Executives review a mysterious drop in yield on those digital dashboards, while the physical cause remains entirely undocumented. Meanwhile, the night shift frontline technicians pull ruined batches at 4 a.m., manually scrubbing the hardware to find the leak. Blind trust in robotic log files over physical reality is the most costly, ignored bottleneck in the modern corporate enterprise. The standard industry reflex is to fix this physical blind spot by adding complex cloud analytics and massive new data infrastructure. This diagram illustrates the problem with that approach. The fast-moving dot shows a robotic armature completing its physical cycle. It finishes long before the cloud server ping, shown by the slower line, completes its round trip. Cloud latency inherently destroys your ability to monitor high-speed mechanical actions in real time. This lag generates noisy, delayed alerts. Frontline operators experience alarm fatigue, and like ICU nurses surrounded by constantly beeping monitors, they routinely ignore them. We can apply the principle of Feynman compression here, cutting through complex jargon to define the absolute basic truth of a system. Stripped of its marketing, a multi-million-dollar pipetting robot is a fast idiot. It executes flawed commands perfectly without ever verifying its own output. Adding centralized cloud computing to a blind machine does not create autonomy. It just creates faster, more expensive, invisible failures. The alternative to this is restorative engineering. This is a shift toward essential, localized design, instead of bloated software layers. The physical intervention requires bypassing new cloud infrastructure entirely. Instead, we attach simple, low-cost cameras directly to the robotic armature. On the software side, we deploy Python-based edgeai vision to process the visual frame locally at the exact point of mechanical contact. This setup monitors tip attachment and plate alignment in real time, with zero latency. The immediate mechanical consequence is absolute control. The machine halts itself the exact millisecond a physical error occurs, before the batch is ruined. Extreme, unobtrusive localized simplicity cures this trillion-dollar blind spot by giving the machine actual eyes. There is a stark contrast between sterile biotech labs and the raw physical reality here in Nagpur. These highly advanced physical inference architectures are designed from this exact remote location. My mother tells her friends that I fix factory printers. She is functionally correct. Implementing advanced AI in industrial settings is just high-stakes mechanical troubleshooting. The true value of an edgeai operator is not writing complex code in a vacuum. It is fixing the physical realities that software ignores. The fully autonomous, self-driving lab is a dangerous myth that executives need to abandon. The required alternative is hybrid human-machine control, powered strictly by local sensing. This operational model eliminates the bioreactor blind spot and protects executive profit margins at the source. Deploying visual edge AI returns operational agency to the frontline technicians, validating the undocumented labor they perform every night to catch machine errors. Never blindly trust an automated system log. To survive the modern manufacturing landscape, you must watch the hardware, watch the hands.